The goal of amplifiers is to increase the amplitude of a signal, and that's because normally when you measure something, it doesn't have a high magnitude, and if it's a high amplitude, and when the amplitude is not large enough, you cannot really use a measurement system to measure it. Or, for example, Arduino will not be able to measure it, so you need it to be of the order of few volts when it is actually microvolts, and so that's the reason why you want to use an amplifier. Okay, so amplifiers are used to amplify signals so that they can be measured. Okay, so before we get into the operational amplifier, let's look at what are the characteristics of a good amplifier. Yes, amplifier, think of it as a block. Okay, any block is going to get, since it's going to be connected in any circuit, it's going to have some current flowing through it. Let's say that in is the current flowing in. I out is the current flowing out. Okay. All electronics devices will have its own impedance. They call it impedance and not resistance because it can have, it can be frequency dependent. That's why I called it impedance. And impedance on the output end, so Z out. And then we have V in and V out. So everything can be thought of in terms of voltage, currents, and impedances. Now, what's going on here is that we are, for an amplifier, interested in V out divided by delta V in. So V out is the output voltage, and V in is the input, and here we're interested in the change in input voltage. So remember, you're using this to take a signal from some sensor on the left side, and then you're trying to amplify it on the outside, on the right side, V out. This ratio is called AV, which is known as a voltage gain. And obviously, because you want V out to be many magnitudes greater than V in, you want AV to be big, right? So think of delta V in the order of microvolts, and delta V you want it to be in volts. So it would be, in that case, AV would be something like 10⁶. Now what we want is this AV, which is the voltage gain, should be ideally linear. Okay, linear means that the ratio is going to be constant, right? And when you say linear, we usually think of it in terms of frequency. So at all frequencies, AV should not change much, okay, which is nice now, because now we can, irrespective of what the input frequencies, we'll always ensure that that ratio is big, and so our measurements, we don't have to worry about AV changing. Okay, now let's look at the other things here, which is the I and I out. Why have I written those things? Now we know that V in divided by I in voltage divided by current is the impedance. And I said that this, well, I'm not written down, but this should be big. Okay. So it's saying that the input impedance is big. Think of impedance for all practical purposes as a resistance. So if the resistance is big, then the result is that the current I in would be small, right? Bigger the resistance, smaller the current. And that's good because if the current is small, then you know that it's not going to suck the current from another sources. Think of this amplifier as sitting uh, with another component, let's say a resistor. And if the amplifier starts drawing a lot of current, then that load or the, let's say it's a bulb or something, is going to get less current, which means it will glow less brightly, and you don't want that to happen. So what you want to do is you want it to have minimal effects on the current of the load which is connected. So having a big impedance means that In is small. And that doesn't affect the load. The current in the load. Okay, so then other thing which is key here is that if you look at the ratio of V out divided by Z out, that's going to be the output impedance. And that ideally should be small. What that means is that if V out is small, then that implies that V out is also small. Okay, that means that for a given change in V in, the output voltage does not change much. And that is a good thing to have because if the output voltage changes by a whole lot, then it's not going to do a good job of amplification. So with this in mind, so you don't really have to worry too much about these things because the op-amp takes care of that. It is a device which has a big impedance, input impedance, and a very low output impedance. So that gets us to an operational amplifier, which is something which we'll be talking extensively here. In short, it's called an op-amp. What is an op-amp? And I'll show you what an op-amp looks like. But before that, it's basically an integrated circuit. Okay, so you'll see that if you open up an op-amp, it'll consist of many resistors, maybe capacitors, transistors, and so on. And I'll show you what it looks like in a bit. Okay, so it consists of resistors, capacitors, bipolar junction transistors, and so on. Okay, and then it is manufactured as a single chip of silicon. Somebody has done the work of putting all these things on a single chip. So you really don't have to worry about wiring it, which is a big problem once you have too many things, too many components to wire up, right? And then it is basically a building block for a host of things which are important for mechatronics. They are amplifiers, which is what we'll be talking about extensively today. They are used as integrators, summers, so integrators are usually associated with differential signals. So when you integrate, say, velocity, you get position and so on. Summer is basically you have two independent voltage sources. You want to add them. That would be a summer. A differentiator So derivative of voltage is acceleration. That's what a differentiator would be. Comparator. If you want to compare two signals, you can do it using op-amp. A to D and D to A converter. So analog to digital and digital to analog converters. And then sample and hold amplifiers. So one of the applications of this would be in a LCD display. When you make it, when you see the LCD